Okay, everyone, welcome back to the last session of the conference. Our first speaker of the session will be Xiaoliang Qi from Stanford, talking about emergent spacetime from generalized free fields.
Okay, can you hear me? No, this is not. Hello? Oh, it's only for recording? So there's no mic for... Hello? Oh, okay, works now. Sorry. Okay, thanks very much for the organizers again for inviting me to this exciting workshop. The topic I talk about is probably a bit different from the main topic of this workshop, but as Ashwin said at the beginning, I think it's a time where many different fields are emerging, and one of them is quantum gravity and quantum information and condensed matter physics. So this I think this work is an example where we were mainly motivated by quantum gravity motivations, understanding emergent space-time, but it also I think has some implications to the general quantum many-body physics. So this is a work in collaboration with my student Tamara Nebabu, and this is a recent paper on archive. I will start with an overview because I think this is not a quantum gravity audience, so I will talk about the overview of this holographic duality and my also share some of my opinion on that, and then we will discuss this particular construction in our work where the goal is to have a more general understanding on why there is emergent space-time for more general systems than we understand before. And then I'll discuss some ongoing works. So holographic duality, in one sentence, it says that we live in a world like VR. So it looks like 3D, but three-dimensional space, but actually the data lives in two-dimensional space. Like there are actually pixels in our world. So that's basically the point of view, right? So, but why? I mean, why is that so natural? So it starts from this black hole, this famous formula of black hole information. So this Bekenstein and Hawking realized that from some thermodynamic considerations, they realized that the entropy of black hole naturally should be proportional to area, and that's also natural because G Newton, if you multiply by the right powers of h bar and c, is a unit of area, right, rather than a unit of volume. So this together with the consideration that black hole is is like the densest thing you can fit into a region of space, because if you already have a black hole in this region and you try to throw more things in, then you just make a bigger black hole, right? So the black hole is like the biggest thing you can fit in this given area. And therefore, it gives you an upper bound of how much entropy you can put in this region. And therefore, the maximal entropy you can put in this region, in any region of space, is proportional to the area rather than volume. And that tells you something very strange is happening, because naively, if you think about a quantum field theory or quantum many-body system, then if you can put a qubit here, you can put a qubit here, you can put a qubit here, and then you can put a qubit anywhere. Therefore, the entropy should scale with volume. So the fact that this is not true is telling us that the degree of freedom we thought to be independent at different locations of our space are actually not independent. Right? So that's the basic idea behind this holographic principle. And later, after 1997, because of the discovery of ADS-CFT, this is not just an observation anymore, but it becomes a theory where we can calculate different things and understand that in this particular case where there is this, you can think it as like probably the holographic principle is true in general, but in these special cases where we are looking at space with asymptotic ADS geometry, then there is a way to anchor the theory. Right? So there is this boundary. So there is a dual theory, which is a quantum field theory living in some geometry. Then there is a way to map between these two theories, and that tells us some more refined comparison and give us some idea why some theory can look local, but actually it's not local. So when we think about this holographic duality between this asymptotically ADS space and the boundary, then duality means everything should have a counterpart. So correlation functions have its counterparts. So like say the boundary, so the first thing discussed in these dualities is the comparison of correlation functions. So if you think about correlation functions of some field phi in the bulk, and then take these bulk points approaching the boundary, then you get boundary correlations. So I don't know what you feel, but like when I heard about these before I started working on this field, it just sounds trivial. Like, okay, what are you talking about? Like the correlation function on the boundary is the same as correlation function in the bulk approaching the boundary? Of course. I mean, we have that in like a condensed matter material when you have correlation functions on the boundary having the same property, right? So of course, so I want to emphasize like what actually is non-trivial here is we are not talking about a theory and its boundary. We are talking about a theory and another theory with one lower dimension. So it's like, think about like the bulk theory as something like a three-dimensional material, and then the boundary theory is not really. I don't really mean the boundary of that bulk theory. I mean like something like a graphene, like one lower dimension. But because it's strongly correlated, the correlation function looks like as if this thing lives on a boundary of something else. So that's why it's a non-trivial thing. Right? So. And then there is this entropy, the famous Ryo-Takanagi formula, which tells us that there is a natural generalization of the black hole entropy formula, which applies much more generally, like the entropy of a boundary region corresponds to this geometrical quantity, which is the area of the minimal surface that separates this region from the rest of the system, which is this gamma A. So the way we understand this is that there are different states on the boundary. The boundary is a many-body system. It has ground states and excited states, and the different states correspond to different geometry. Right? So you could have excited state which looks thermal, and that corresponds to black hole geometry, and the ground state looks like a ADS geometry, and the excitation near the ground state may look like some particles in the ADS. Right? So this duality is like between geometry and states, and roughly speaking, the scale, like the vertical direction, the new emergent direction, you can think it as corresponding to some length scale, so that like if you have some particle falling into a black hole, from the boundary point of view, what happens is that some local perturbation becomes more and more non-local and eventually spread to the whole system, which is nothing but thermalization. Right? So if you have a particle falling into a black hole, it corresponds to thermalization on the boundary. So that gives us some intuition. So to help us understand better, I feel like it helps me understand this thing better by comparing it with something in condensed matter. So I would like to compare the holographic duality with like mean field theory, which we are familiar with. For example, let's think about BCS theory. So for simplicity, let's think about a neutral kind of superconductor, which means I'm talking about superconductor, but I'm not thinking about like Higgs, like this kind of mechanism. Let's just think about I'm having something like helium-3, like I'm having fermions with interaction. So this macroscopic theory is like fermions with 4 fermion terms, and that's like the analog of like this boundary theory, which is super-Yang-Mills theory, or the SYK model I'm going to talk about later. So like there's some many-body system in the case of holographic duality. Then I think, so say in the case of interacting electrons, we can do some mean field, and if you want to justify your mean field theory as some controlled limit, then the way you do it is you should do larger n. Right? So you introduce n flavors, and then in the limit where n is big, mean field theory is controlled. Right? So you get the mean field theory, and the mean field theory tells you to the leading order, it gives you the order parameter, and then once you solve the self-consistent equations, you get the order parameter, then that determines the quasi-particles. And then if you go one more order, then you can think about fluctuations about order parameter, which gives you Goldstone modes. Right? So these are like consequences of this effective theory. But then you can also go further, like you can do a long wavelength limits and near the phase transition, so you can derive this kind of like 5-4 theory, effective theory. So I think what we are looking for as a quantum gravity theory in this holographic duality is the same kind of structure. Like starting from some macroscopic theory, we hope we could derive some theory which is the analog of the BCS theory, and that theory should have like some the analog of the other parameter is the geometry itself. You have ideally you want like start from your boundary theory, you solve that background geometry, and then what's the excitations on top of that geometry? It's the analog of like the Bogoliubov quasi-particles, which are like matter fields living on that geometry. And then the fluctuation of that geometry is like graviton, right? So which is like the Goldstone mode here. So really it's everything in parallel, and then under certain limits, maybe not generally, but for some systems, there is a long wavelength limit of that theory, which becomes like the Einstein gravity, hopefully, or it becomes something else, right? Einstein gravity plus some other corrections. So I think the key thing that's missing is we don't really have a derivation from this many-body theory to this theory that we can derive these kind of things from it, and that's related to the goal of this work. Yeah.
I don't know about derivation, but isn't string theory the thing that goes in the green box?
It's more like this, right? So the question is whether the green box is string theory. I thought, well, I don't know. I thought string theory is supposed to be like the theory that gives you all these things, right? So I thought it's like this.
Well, I mean, that's like the theory.
This is like the super-Young-Mears, yeah. So in the case of super-Young-Mears theory, this is, yeah, I mean, in the sense that it's something that contains the gravity theory, but also contains other higher excitations, it's something like this, yeah.
You want something sort of that is less than the full string theory.
Well, I think the one question is whether, as we will discuss later, like the lesson we learned from like tensor networks and like SYK models, the question is whether this is something beyond that one particular example of a supersymmetric like Young-Mears theory, right? So I mean, it's like this emergent space-time is probably something for generic many-body systems. So like just like mean field theory, right? You could have this method which you can apply to different kind of many-body systems. Right? So that's what we hope to talk about. Yeah.
So you can do some, to answer the question partly, you can do some bulk reconstruction from the boundary, extending the bulk, but mostly people have only done it in 3 dimensions. It's been very hard to do beyond 2.
Okay. We can talk about that later. Yeah, I guess that's a comment that we can do some of this construction in 3D. Yeah. So this is to explain the motivation, and then so the message, like the concrete thing we did towards this direction is we want to show that for any given generalized free field, you can map it to a geometry in the bulk, and we are doing it in the just mathematically. Like I think this doesn't necessarily require discretizing time, but to do this numerically, we only know how to do it with discretized time. So it's a mapping between some dynamics at a discretized time for a generalized free field, mapping that to a free fermion in the form of a Gaussian quantum circuit. So and the thing we want to emphasize is that this approach applies to all generalized free fields, which I'm going to define in the next slide. It applies to all generalized free fields without assuming like conformal symmetry or anything else. In that sense, I think that's more general than what we already know as holographic duality. So that's, I mean, what we did is a generalization of this approach called HKLL, which probably is the earliest way people try to write down the mapping between operators in bulk and boundary. And the idea is that it's like, roughly speaking, it's like an equation of motion along, it's like a Green's function in the spatial direction. So the original HKLL was like you already know the equation of motion of a bulk free field, and then you can use that equation of motion to relate a field and its boundary value. and then you promote that into an operator equation, then because the equation of motion is linear, you get a linear equation. Right? So you get a bulk field is equal to some linear superposition of boundary fields which are space-like separated from it. So it's similar to the Green's function, except like you are not propagating in time, but you're propagating in space. And then the thing we get is similar, but the logic is very different. So the thing we want to emphasize is that we obtain a similar kernel completely from the boundary data. So start from the boundary, we totally don't know whether the bulk is ADS or anything else. The only thing we assume is this causal structure, and then you can derive the kernel and the dynamics of the bulk all from the boundary correlation. Okay, so to discuss that, let's first define generalized free field. So generalized free field really means anything that satisfies the weak theorem. So more precisely, it means if you introduce a source term for your field, then the source term has the generating function which is quadratic. And once that's true, then all the correlation functions are determined by the two-point function G. So this is the example of fermions, and we can also talk about the same for bosons. So we are going to focus on the fermion example because SYK model provides a very nice example for that. So this really doesn't depend on conformal symmetry. And okay, so just to have a concrete example, the example of generalized free field is this Sachidev-Ye Kitaev model, Subir and Jinwoo Ye proposed in 1993, and related to gravity by Kitaev's work around 2014. So it's an interacting Majorana fermions, with Q-body interactions, and then you have n Majorana fermions, and we are thinking about the large n limit. So the relevant derivation that tells me it's a generalized free field is that you can introduce this two-point function and basically use that as an order parameter. And in the large n limit, the two-point function is determined by these string Dyson equations, and the fluctuations are suppressed by 1 over n. So there's many other nice properties, like there's this maximal chaos, right? The fluctuations gives you a quickly growing Lyapunov exponent. But for the purpose of this talk, we will focus on the two-point function, which is, so the only thing we need is the fact that higher point functions satisfy weak theorem, and it's all determined by the two-point function. And okay, so two-point function, for example, for a thermal state will look like this, and it's decaying. And then you can generalize the model. You can, for example, you can have multiple SYK sites. You can couple them either by the same kind of random coupling or by something like a bilinear coupling. Right? So there's many different ways to couple them, which still preserves the fact that you have generalized free fields. Okay, then what do we want to do? So the key of our construction is rely on this observation that if you look at single particle operator, let's think about states, right? So let's say I have a state which is like, for example, the ground state or like thermal field double state. And so there is a reference state because when you define weak theorem, that's defined in respect to a state, right? Ground state of free fermions is an example where you have weak theorem. Right? If you talk about excited state, it will not satisfy weak theorem. So you have a reference state, and then you apply a single fermion operator, you get these single particle excitations, and they form a linear space. And now, if you define this linear space of single particle states labeled by time t, which means these are single particles at time t, then the key difference I want to emphasize is the key difference between free theory and the generalized free theory is that although both of them satisfy weak theorem, for free theory, this Vt doesn't depend on t, because at all different time, single particle states evolves to single particle states. So the space of single particle states doesn't change. But for generalized free field, the Vt and Vt prime are different. Single particles doesn't stay single particles, right? So that's the key, yeah.
So in the context of CFT, we know that a single free field in ADS corresponds to a generalized free field on the boundaries.
Yeah, yeah.
And for generalized free field in CFT, we know the difference compared to ordinary free field is that there's a free parameter, the scaling dimension. How is that related to this independence?
Yeah, good question. Yes. So in the special case of CFT, the anomalous dimension, the fact that the scaling dimension is not integer, directly translates to the fact that if you compute if you compute this anti-commutator matrix, and then what happens is that when the scaling dimension is not integer, then this anti-commutator matrix will be non-singular. The determinant will be non-zero. But for free field, sorry?
What about half integers?
Well, I mean, for fermions, it's probably half integers, but
they're bosons. So you could have free scalar field with half integer scaling.
So I think maybe a more precise way of saying this is if you look at the Green's function, if it has poles, then it's free field. Right? If it's branch cuts, then it's a generalized free field. And that difference translates to that statement, directly translates to the statement whether these VTs are the same or not. So like when I say this space of single particle states at different time, they are different spaces, that translates to the statement that the anti-commutator in the fermion case or the commutator in the boson case, that when you view that as a matrix, which means like the time, the t prime is like entries of the matrix. Like I'm looking at all different time. Let's think about a discretized picture. So t is like a discrete variable. So you look at all different time, and if you have a flavor, you look at different flavors. Then this is a matrix which basically tells you, it defines an inner product in the space of the union of all the VTs. And the difference between free and the generalized free field is for free fields, you just pick any two time, and these two spaces are the same. So therefore, this inner product is singular, means the determinant is zero. Because the field here, like the single particle states here at different time, is a linear superposition of the field here. And for generalized free field, that determinant is non-zero. And that's the difference between the pole and the branch cut in the case of CFT. Because pole basically means for any given momentum, there is a fixed energy. And for the branch cut, it means for a given momentum, there's still a continuous spectrum of energy. Yeah. So what we're doing is exactly saying all these things still survive, and you can still study all these without conformal symmetry, without anything. Yeah.
On 2 slides ago, you had a comment about the expectation for the gravitational SYK. Can you remind me, is that Jacob tidal gravity, is it supposed to be built to only singlets states of SYK, or or the single particle states that you create, are they included in that?
That's a subtle question. Yeah. The question is whether the duality between SYK model and the Jacob Teitelbaum gravity, whether in that duality the bulk only has singlet field. And I don't think it's clear. I mean, it's like I have this field, which if I map this free fermion, if I map the generalized free field of fermions to the bulk, it will be a free fermion in the bulk. And we kind of think there is this free fermion in the bulk. But you could also insist to describe everything in terms of the singlet field, which are like bilinears of the fermions. And these two seem to be equivalent.
It's in addition to the gravity.
SYK model has many operators, including
Yeah.
which is not part of JT gravity.
Yeah.
The only thing is the lowest singlet.
Yeah, like if you insist to use singlet, you'll see a tower of all these higher things. But they can also be described by this fermion. I mean, part of the effort here is trying to derive that instead, like trying to derive what happened to this fermion in the bulk for the more general case. Because like the duality we know discussed in SYK was only for the low temperature limit where there's this emergent conformal symmetry, right? But the approach here I'm describing only depends on the generalized free field, so it doesn't depend on the low temperature. I think I will only have time to quickly skip over the results. But but I want to emphasize that as you see from this general construction, like in the end, the only thing I need to do is a QR decomposition. It's like you have all these spaces defined at each time, and then what are the bulk fermions? The bulk fermions are obtained by orthogonalization. Means this one here. So the bulk we obtain is a quantum circuit, which, by the way, you could take as an assumption, or you don't have to assume it. If you assume this causal structure, means the bulk fermion only depends on bulk boundary fermion here, you can actually derive that the bulk must be a quantum circuit like this. So the bulk fermion here is just the boundary fermion itself, and then this bulk fermion is what you obtain by taking this boundary fermion at an earlier time and orthogonalize with the boundary fermion here. And then this one is you take this boundary fermion and orthogonalize with these two. So you just start from the boundary and just continue orthogonal.
Quantum circuits are all bosonic, so how do you get fermions here?
Well, it's a Gaussian quantum circuit. It means it's a free fermion system where every gate is an exponential of bilinears of fermions.
So does the bulk geometry depend on the scale dimension of the size?
Sorry?
The bulk geometry. So does it depend on scale dimension of chi?
Yeah, well, we don't have a definition of scaling dimensions because it's not conformal field. It's general.
For different Q, there's a scale dimension.
Yeah, if you talk about low temperature, yes. But the more general thing is the whole like 2-point function that determines the bulk. So yeah, so certainly the bulk geometry will depend on A, which in particular means if A is a power law, it will depend on scaling dimension. But that's only a special case. So you see from the procedure, it depends on A. Because A is the inner product. Like these spaces are not orthogonal, so I'm orthogonalizing this. So in the end, what I'm doing is I'm just taking A minus 1/2, taking the matrix A minus 1/2, and then do a QR decomposition. And that gives me the kernel K. So the kernel K determines the bulk fermion in terms of boundary fermion. And once you determine the bulk fermion, you also determine the bulk dynamics. Because say that's the next slide picture. So say every bulk fermion is a linear superposition of the boundary fermion. Right? So if I know this one as a linear superposition of the boundary fermion, I know this one also, and I also know these ones, then I know this gate as a linear superposition. Because remember, everything is Gaussian in the bulk. So when I say I know the gate, I just mean I know the single particle like linear transformation, which take these inputs to these outputs. So everything is determined by A. So you give me an A, I can run this mechanism and then give you the bulk gates. So in the case of SYK model, because it's diagonal in this IJ, in this flavors, so it's like effectively it's like there is only one Majorana fermion at every side. Although actually there's n, but everything is diagonal in the I index. So the gate is just an orthogonal transformation of these two Majoranas. So there's only one parameter, which is the angle, the mixing angle. So okay, so now we are ready to show the results. And how many minutes do I have? Maybe.
-4, but
okay, sorry. I started a little later, but yeah. So this this is what happens to the gate angle, right? So when you go in, the gate angle quickly approach pi over 2. And what is special for pi over 2? It means that the right mover and left mover doesn't couple. So you see what happened is there is this semi-infinite circuit with this thing as my boundary. And then what happened is the particle goes in and then just stop coupling with the left mover. But that's exactly what you expect when you have a black hole. Right? The black hole horizon is playing the role of a bath. The particle goes in and doesn't come back. And then in this, if you already know there's a black hole, you would say the boundary has correlation function decay exponentially because there is this path. Things go away and doesn't come back. And then here we are just saying you can reverse that logic. You start with this exponentially decaying correlation function. You can construct that path, and that construction is actually unique. You construct that whole bulk geometry, and the key thing is that these things were not even defined before because the correlation function is not conformal, it's not close to anything with a dual. But now this definition makes them all meaningful. And then there's, of course, and then once you define that, there's a lot of interesting things you can compute, like the bulk fermion state and the bulk fermion correlation function. And you can take the continuum limit and compute the geometry, because I know the dynamics of the bulk. So let me fit that dynamics to a geometry, to like fermion in the curved space. You can calculate the geometry, and you can actually see how the curvature approach -2, which is what you expect in at low temperature. But that's the nice thing. Like if you choose a different kind of 2-point function, you could get other geometries. It doesn't have to be ADS. Right? So you can get different kind of geometries. And then one funny thing is that the black hole horizon, you can study the fermions at the horizon, and you see that the dynamics at the horizon is actually completely universal, because the kernel itself depends on the boundary correlation function. So all the properties of the boundary correlation actually got canceled by the mapping itself. And as a consequence, this modes at the horizon always looks like a perfectly linear dispersing Majorana fermion, as you expect from a Lorentz invariant theory. So, and that actually only depends on KMS condition. So that's another thing which we found quite interesting. And then you can apply this approach to many other situations, which include like thermal field double state and the shockwave geometries where you obtain by perturbing the thermal field double state. You can apply it to like traversable wormhole where the space is supposed to end. Right? You can just automatically apply that and you read out that the space ends rather than assuming that. And the reason why the space ends is that after some time, the approach failed to work because the modes come back to the boundary. So if you include a bigger energy window, time window, the geometry just, the boundary degree of freedom starts to repeat itself. Right? So the determinant of A becomes 0. Okay, I should end here. And in summary, we show that there is this general procedure turning the correlation functions of the boundary into a bulk geometry. And that's like the mean field. Remember that comparison with BCS, right? Of course, the interesting thing about gravity dynamics is like fluctuations of that, which will tell us whether it's gravitons or something more non-local and so on. And that will be like the next order, right? the 1 over n corrections. And that's all. And one thing related to condensed matter is we think this may lead to a new way to derive hydrodynamics, because this mathematical structure is very general. For any, like, as long as you have a linear space defined for each time and they are not orthogonal, you can run the same procedure. So in particular, if you think about correlation functions and you orthogonalize them, you can get, for a general many-body system, you can get like bulk, you can define these kind of operators which goes away and have no correlation with the simple operators. And that's exactly what we want to throw away when you try to derive some hydrodynamics descriptions of the system. And that's what we are doing now. So this is not, when you do this, it's not specific, it's not restricted to generalized free field anymore. Okay, sorry for going over time. Thanks.
Okay, thanks, Xiaoliang, for the cool talk. So one quick question, since we have a hard cutoff of live streaming at 5.
Yeah.
Andreas?
Yes.
I was thinking that to get a good holographic description also would be good if not just that I have a geometry, but I have a local description in the body that sort of have any hope of ever getting gravity out. You will need local interactions, and you're never going to see this at the level of free field, right? The 1 over n corrections are what makes and breaks the story. And most field theories will not have the gravity to do it. There will be a few very special ones where you actually have a good holographic tool. So I think that geometry
Yeah, so that's Andreas' comment is that most systems you don't expect it to have gravity due because the bulk theory won't be local, and you can only see that in the level 4-point functions. So, yeah, so I agree. I think what this setup will tell us is how non-local it is. I mean, like it's like telling me, okay, at 2-point function level, I can always find this local theory, even if the boundary is nothing close to a conformal symmetry or anything. So it gives me a general background. And then on top of that, if we study the 4-point function, we can tell, like maybe in certain limits, it becomes a local theory.